In this third part of our calculus explorations, we explore the area of circles. I should say that this video was sparked by a discussion I had with Paul Hudson when in my solution I reached for the apothem. So anyway, we want to calculate the area of a circle of radius r. Something like this. Suppose we can measure the circumference. So we can draw a circle and we can walk around it somehow. So I've got this circle and we're just going to walk around it. Maybe our measurement is such that we can see it's a little greater than 6 1/4 times the radius and a little less than 6 1/3 times the radius. If we're really good, we realize that it's 2 pi r. But what about the area? We can't really walk around that. So maybe we divide our circle into 3 even bits and we draw this triangle. It's an equilateral triangle that is the biggest it can be and still fit inside the circle. This is an inscribed triangle and we can see that it's too small. So let's draw the equilateral triangle that is small enough that the circle just fits inside of it. It touches 3 sides. This is the circumscribed triangle. And we can see that that's too big. This is setting up a Goldilocks and 3 bears situation. Instead of a triangle, let's try a square. This looks a little closer on the inside and a little closer on the outside. Maybe one more. Let's try a pentagon. Notice each bit is much smaller, but there are more bits. Even so, the amount that we differ feels like it's getting closer, both from the inside and from the outside. So we notice that as the number of sides n increases, the area of the inscribed n-gon and the circumscribed n-gon, they get closer to each other, and all the time the area of the circle is trapped in between. So we're getting closer to the circle's area from the outside and from the inside. Let's simplify this and just forget about the outer n-gon and worry about the inner n-gon. As the number of sides increases, the area of the inner n-gon gets closer and closer to the area of the circle. But what's the area of this inner n-gon? We split the n-gon into equal triangles. For example, for this pentagon, we find the center, and then we draw the lines from the center to each of the vertices of the n-gon. There are n of them, so let's just focus on this one triangle and see if we can find the area of this triangle, and then multiply it by n to get the area of the polygon. The area of a triangle is, of course, base times height over 2, and so we have to figure out the base and the height of this triangle. The only thing we really know about it is this is the radius, and the other thing I guess we know is that this angle phi is 360 divided by the number of sides, n. And so if we drop this perpendicular so we have 2 right triangles, this is h, the height, and this theta is half of phi, and so this theta is 360 degrees over n all over 2, and if we express this in radians, theta is pi over n. Think about your trigonometry. H is r cosine theta. Theta is pi over n, and so we get that h is r cos pi over n. Don't stop. It's about to get good. Oh, and we're not going to calculate the base. We're not going to bother. So that means the area is half the base times the height, and subbing in for height, the area is base over 2 times r cos pi over n. So what's the area of the n-gon? It's n times the area of the triangle. That's this, and I'll move the n over and write it like this. That looks like a mess, but let's check it out. If n gets really big, what happens to h? Let's follow this progression. The white line is that apothem that I mentioned before. It's from the center to the midpoint of one of the sides. So here's the apothem for 3, 4, 5, 6, 7, 8, 9, 10. And as you notice, as n gets bigger and bigger, what happens to h? H approaches the radius of the circle. Depending on what trig you remember, we could also see this algebraically. If h is r cos pi over n, as n gets really big, pi over n goes to 0. And the cosine of something going to 0 goes to 1. And so h gets very close to r. Okay, that's h, but as n gets really big, what happens to the area of the n-gon? We saw that this piece, the height, approaches r. What about the rest of the formula? Well, this bn, it's the base times the number of sides. That's just the circumference of the n-gon. That's this piece. And as n gets really big, this approaches the circumference. So bn approaches 2 pi r. Cancel the 2's, multiply the r's, and we get that the area is pi r squared. Isn't that nice? Now there are other nice proofs, but I like that. It's an intuitive exploration of limits to get to the area of a circle. And that's part 3 of our calculus explorations.